Okay, so let's first review what we learned last week, okay? So last week we mainly discussed graphical degree sequence, okay, or the graph realization problem. So in this problem, you're given a degree sequence, okay? And your goal is to determine whether there's a graph that can realize the degree sequence, okay? So by realizing the degree sequence, this means you can find a graph such that the degree sequence of the graph matches the input, the given degree sequence, okay? So not every degree sequence is graphical. For example, we consider degree sequences like this 3 followed by 3 zeros. So this one is not graphical because if you have a degree of 3 and you have 4 vertices, then you cannot have any degree zeros in your graph, okay? So every degree should be at least 1, okay? And there are degree sequences like this with total sum, okay? The total degree is not even. So in this case, this cannot be graphical either because the total degree must be an even number, right? So there's a very simple relationship between degree or the total degree and the total age, okay? So the total degree is just twice the number of edges. So this means the total degree must be an even number, okay? So this can be used as a simple check, okay? So given a degree sequence, there's some sanity check you can use to determine whether it is not graphical, okay? But this does not cover all the possible cases, okay? So for example, like this 1, 3, 3, 3, 1, there's really no simple check that you can use to determine that this is not graphical, okay? So that's why we consider an algorithm, okay, for this graph realization problem. Okay. So today we're going to continue our discussion on this algorithm. So first of all, we're going to show that this is correct in the sense that if the algorithm outputs a graph, then this indeed realizes the input degree sequence, okay? On the other hand, if the algorithm returns not graphical, okay, then indeed this is the case that the input degree sequence is not graphical, okay? So, so what this algorithm does is that, well, because if the input degree sequence is graphical, we also want to have the graph, okay? So we're going to first create vertices, okay? So this one is simple because just by looking at the degree sequence, you know the number of vertices in the graph, okay? So if the degree sequence has n numbers, this means you have to create n vertices, okay? And also we have this remaining degrees, okay? The remaining number of edges you should have, you should add to the vertex vi, okay? So initially, this is just di. Di is just input, okay? So this means for the ith vertex, we should have di edges incident to it, okay? And then we just repeat the following steps, okay? So in every round, we're going to first pick a vertex, okay? for this algorithm description, we can actually pick any vertex, okay? So you can pick like the first vertex, or you can pick the last one, okay, it doesn't matter, okay? So let's call this Vj, okay? So according to our definition or notation, okay, we have to create Rj edges, okay, instant to Vj. All right, so for example, like this one, and say we first pick V3, and since, so this is V1, V2, or D1, D2, D3. So D3 is 2, which implies that we have to add 2 edges to V3, okay? So let's step A, okay? So the most critical step for this algorithm is how we create the edges, okay? Or how do we pick the endpoints for these Rj edges, okay? It turns out that we have to pick the endpoints with the highest remaining degrees, okay? So last time we've also considered like a failed algorithm, okay? So the algorithm fails because if we choose the vertices with like the fewest remaining degrees, then the algorithm fails because in some future round, you may run into a situation where you cannot find enough endpoints for your Vj, okay? So I want to make sure that in the future you can have more vertices you can choose as endpoints. So we're going to choose the vertex with the highest remaining degrees, okay? All right, and that's basically what this algorithm does. So we just connect this Vj and the vertices picked in step B, okay? Create edges and update the remaining degrees, okay? So for Vj, okay, because we've created Rj edges for it, so the remaining degree will be 0. Okay, this one, okay? And for the vertices picked in step B, because we create 1 edge for it, so the remaining degree is reduced by 1. Okay. All right, so I think we can apply this algorithm to this example again. So step A, we pick V3, and we're going to look at the degree sequence and choose the 2 highest degrees, okay? The reason it's 2 because V3 has the degree of, has a remaining degree of 2, so we have to find 2 endpoints, and those 2 endpoints must have the highest remaining degrees, in this case, V1, V2, okay? And then we just create edges and update the remaining degrees, okay? Oh yeah, so this row is the remaining degree, okay? So after we do this modification, R3 becomes 0, and R1 and R2 become 2, okay? Okay, one more round. Suppose in this round we pick V5, okay? So Vj or J is 5 in this round. And the remaining degree is just 1, okay? So we only have to find one neighbor, okay? I think if I remember correctly, this should be like a failed example because, yeah, okay. So if we connect V5 to V4, this is not correct, okay? So this is just for the purpose of demonstrating what happens if we do not connect V5 to V1, okay? So what happened is that No? Oh, no. Sorry. So this is not, so these degrees are after the modification, okay? So to find out which one should be the correct endpoints, we should look at this degree sequence, okay? So we pick V5, and we have to find the largest degree, okay? The single one largest degree. So now we have ties, so we can choose from V1, V2, and V4 because they all have the highest degree. So in our previous example, we choose V4, which is fine because it has the highest degree, okay? Sorry, okay. So this step is correct, okay? And after we add the age, after we modify the remaining degree, this is the new degree sequence. Sorry, okay? All right. Okay, so let's the algorithm, okay? Are there any questions? 有问题吗？我刚记错了 ，OK， 我刚以为这边我们在选，我刚以为我们在选这个 Step B 要选 endpoint 的时候，我以为是根据这个 degree 选，但我刚刚记错了 ，OK， 这个是我们修改完就是加完 H， 然后修改完 remaining degree 之后新的 degree，OK， 所以我们真的要看的话是要看这个 ，OK， 所以 V5 在选的时候，它就会选到，它可以选 V1、V2 跟 V4。我们上一半例子我们选 V4，OK， 有问题吗？ Okay, so today our first goal is to show that the algorithm is correct, okay? And to do this, all we have to do is to show that whenever we try to reduce or simplify the degree sequence, the answer still remains the same, okay? So this means if this, so D is the original degree sequence, and D prime is the degree sequence after we pick Vj and we pick all the endpoints for Vj and connect and add all these edges, okay? Okay. So this is the original degree sequence, and this is the new degree sequence after one round, okay? So the new degree sequence, so for this D prime, we assume that for step A, we always pick the degree, the vertex with the least degree, with the smallest degree. So this is why Dn becomes 0, okay? Because we're going to find all the neighbors for Vn. So after a round, the remaining degree will be 0, okay? And when we find endpoints or find neighbors for this vertex, we always choose the largest degrees, okay? So for these degrees, their remaining degrees will be reduced by 1. So we get D1 minus 1, D2 minus 1, D3 minus 1, up to D delta minus 1. So here delta is just the smallest degree, okay? And all the remaining degrees are the same, okay? So we want to show that if this original degree sequence is graphical, then it is the new degree sequence is still graphical, okay? So I think last time Melvin asked, okay, is it possible that the algorithm outputs no, it's not graphical? Well, the true answer is it is graphical. So to avoid this like bad or wrong behavior, we need this, okay? Because if we can show that if the original degree sequence is graphical, then the new degree sequence must be graphical. Then this avoids what Melvin mentioned, okay? 所以这边最关键的就是，如果本来的它是 graphical， 就是真的有一个 graph 可以 realize 它。我们这边做的事情是确保说新的 degree sequence 也是 graphical， 那这样就不会让那个 Melvin 上礼拜说的那个，就是有没有可能这个演算法它 output 是不是 graphical？OK， 但事实上它其实是 graphical。那这个如果这个是对，就是上面是 graphical， 新的也会是 graphical， 就不可能让这件事情发生。OK， 所以这是整个证明最重要的地方。OK。Okay, so this is like the first direction. So if the original one is graphical, then the new modified one or simplified one is also graphical. Okay, but also we need to consider another direction. That is, if the original degree sequence is not graphical, okay, so the answer is no. Okay, we have to make sure that after we simplify the degree sequence, the answer is still no. Okay. So this is actually equivalent to this statement. Okay, so okay. So these two statements are equivalent. Okay. The reason is that if P then Q, so this statement is equivalent to if not Q, then not P. Okay. Okay. And the reason that we choose to prove this instead of this is because if the degree sequence is graphical, then we know that there must be a graph that we can use, okay? The graph that realized this one, okay? But if you tell me that some degree sequence is not graphical, then it's, I don't know how to start a proof, okay? Because I have no graph to start with, okay? So that's why we will prove this instead of this, okay? Because now we have some handle we can use. We can have at least some graph to start the proof, okay? So really what this slide shows is that we do not change the answer, okay? So if the original answer is yes, then the new answer will still be yes, okay? And if the original answer is no, then the new modified or simplified degree sequence also has the same answer, no, okay? Okay, so we're going to prove these two statements, okay? So as a warm-up, we will prove the second one first, because it turns out that this one is easier, okay? Okay. So what is the setup? Okay, so recall D prime is the simplified degree sequence, okay? And D is the original degree sequence, okay? Okay, so this is our setup, okay? Okay, and the assumption is that the simplified degree sequence is graphical, okay? So this means we can have a graph, V1, V2, okay? So V1 has some edges, V2 has some edges, okay? And the degree of V1 is D1 minus 1, and this is D2 minus 1. Okay. So notice that Vn has no neighbors, okay? It has no instant edges because for D prime, the smallest degree is 0, okay? Recall that this is because it's like the idea that we get D prime is that we will create edges for Vn. Therefore, the remaining degrees will be 0, okay? So that's why we have this 0, okay? Okay, so this is a graph that realizes D prime, okay? Okay, so this is the assumption, okay? We get this assumption because D prime is graphical. Therefore, we have a graph that can realize D prime, okay? And our goal is to show that the original degree sequence is also graphical, which means we have to create a graph, okay? We have to create a graph such that the graph realizes the original degree sequence. All right, so the question is how, okay? So how can we create such a graph that can realize the original degree sequence? Now we can see the main differences are that, so first, for like the first delta vertices, their degrees must be increased by 1, okay? So this one is D1 minus 1, and what we want is D1, okay? So it's like we have to create one edge for V1. Similarly, we have to create one edge for V2 up to V delta, okay? So for these vertices, we have to add one more edge. Okay? So this is like the first difference between D and D prime, okay? And the second difference is that the last one, okay? So the last guy for D prime has degree 0, but in our new degree sequence, this one should have degree delta. In other words, we have to add delta edges. Okay. All right. So how to add these edges to like satisfy these two constraints? 我们有两个，应该说现在只有一个图 ，OK？ 所以这个图它现在它可以去满足旧的，不是满足这个比较简单的 degree sequence，OK？ 下面这个。那我们要满足的，我们现在的目标是要去满足这个新的，我一直讲反，这个原来的这个 degree sequence，OK？ 然后新跟旧的差别就是我们手上有的这个，它的 degree sequence 有点像比较小一点 ，OK？ 对前面的这些点来讲，它的 degree 都减一，然后对最后面这个 degree， 它甚至只有0 ，OK？ 那它一个邻居都没有。那如果你要可以想办法满足这个 original degree sequence 的话，这前面的这些点呢，每一个点它都需要 degree 要再增加1。换句话说，你都需要帮它加一个 edge，OK？ 然后最后一个这个 edge 最后一个这个 vertex， 它 degree 本来是0，你要帮它加到 delta。所以现在的问题是你要怎么加这 delta？ 帮这边加 delta 个 edge， 然后帮前面这个每一个人都加一个 edge。这个 edge 要怎么加才可以满足上面的限制？所以这个问题很简单。所以如果你现在没有 idea， 就代表问题在我身上，代表我们要把问题讲清楚。Exactly. Okay. So, but before I repeat Melvin's answer, I want to make sure that all of you understands the question. 所以有人对这个问题是不是很了解的吗？因为我们今天会继续讨论 degree sequence， 所以我想要确定大家都了解这个问题。然后某种程度，如果你不知道这个要怎么做，我刚刚说的极大可能性是因为我们要把题目讲清楚。所以我不确定，比如说一修，你知道现在在问什么？这样 ，OK， 那你知道怎么做 ？OK， 所以因为人很少，我应该可以试着尽量记得大家的名字。所以同学叫什么名字 ？Sorry， 可以大声一点。思雨 ，OK， 所以思雨，你知道这个在问的问题是什么 ？OK， 所以那你知道要大概怎么做吗？思雨 ，OK， 那后面那同学叫什么名字？陈什么？ 组合，组成哦 ，OK， 所以组成你知道这是什么意思吗？在 OK， 组成施语，然后正号。大家不要对我的记忆力太有信心，我可能下一节课我就会忘记，但是尽量记得 OK， 好，所以如果大家都有知道这问题在问什么的话，我们就继续了 OK。All right, so really this is not difficult at all. Okay, so to satisfy these two constraints, all we have to do is to create edges between Vn Vn and V1, Vn and V2, Vn and V delta 1, minus 1, and Vn V delta, okay? And then we're done, okay? And then we get a graph that realizes D, okay? So the proof is simple, okay? So it's easy to show that if D prime is graphical, then the original degree sequence is graphical. And recall that this is equivalent to this, okay? So if the original degree sequence is not graphical, then the new degree sequence is not graphical, okay? So in some sense, we preserve that if the original answer is no, okay, meaning it's impossible to create a graphical, it's impossible to create a graph to realize it. Then after we simplify it, after we do a round, the new degree sequence is still not graphical, okay? So I think this relates to the fact that if the graph, that the algorithm produces a graph, okay, then the graph must realize the original degree sequence, okay? It cannot be the case that we create some weird graph which cannot realize the original degree sequence. It's impossible, okay? Because if we create a graph, and so this means we say that the original degree sequence is graphical, okay? But this graph is not correct, okay, in the sense that it cannot realize the degree sequence. This must imply that this is wrong, okay? Because during our transformation, it must be the case that the original degree sequence is not graphical, but somehow after we simplify it, it becomes graphical. Therefore, we can create a graph, okay? But since now we have this proved, so we cannot have this kind of weird behavior, okay? 所以我刚刚想要说的是，这件事情刚刚我们说的，其实就是说，如果本来的是做不出来的，我们绝对不可能突然间演算法可以生一个 graph， 可以说 claim 说这个可以 realize，OK？、所以换句话说，就是只要我们有生 graph 出来，它就一定会 realize 本来的 degree sequence，OK？、对，大家可以再回去想一下 ，OK？ 所以因为如果本来的是不可能存在的，然后突然间的演算法可以生一个图出来，那就一定代表说在中间的某一个步骤，我们把本来不是 graphical 的变成是 graphical，OK？、那这件事情是不可能。Okay, now the first one, okay? Okay, so for this one, we have a graph that can realize the original degree sequence, okay? And I want to show that the simplified one is also graphical. Okay, so now I'm drawing a graph that realizes D, okay, the original degree sequence. Okay. Okay. Okay, so this is a graph that realizes D, okay? Now our goal is to construct a graph that can realize D prime, okay? So once again, we should focus on these two sets of vertices, okay? So this is like the other direction, okay? So now, the degree is like too high, okay? So in the previous case, the degree is too small, and we want to create more edges. But now the degrees are too high, and so we have to remove some edges instead of adding edges, okay? So it's like we have to remove one edge from each vertex, okay? And for Vn, because now the goal is to make the new degree 0, okay? So we have to remove all the edges. Okay. So similar questions, okay? But instead of adding edges, now we have to remove edges. So how to remove edges? I think I should add more red edges, okay, to Vn. Okay, because the degree of Vn, that is the number of edges for Vn, should be equal to delta, okay? Because recall that Dn is delta, okay? So if for this box we have 5 vertices, then Vn should have 5 edges. Okay. And also we assume that dn is greater than or equal to dn minus 1 and so on. Okay, so this is in non-increasing order. All right, so to make this graph more realistic, we actually add more edges. Okay. Okay, so this guy, so this one has the highest degree. Okay. So this one has the second highest degree. Okay, and this one has the smallest degree. Okay. But our setup is that Vn has a degree of delta, and we look at the highest delta degrees. Okay. Okay. So how to remove edges? Well, there are two cases. Okay. So the first one is very easy. Okay. So what if I tell you that Vn is adjacent to Vn minus 1, Vn minus 2, down to V delta. In other words, so this is case 1. So for this case, the neighbors of Vn are precisely the vertices in this box. Okay? No more, no less. So, how to remove edges if this is true? So, case 1, Vn is adjacent to V1, V2, down to V delta. And the goal is to have a graph that realizes D prime. Yes?是说，你说为什么可以这样假设吗？你是说为什么会突然有这些绿色的边吗？哦，sorry，我写错。哦，抱歉。哦，所以我刚刚前面就写错了，是不是？看一下。OK， 这一样是delta。OK。对，谢谢。所以 yeah, so these are V1, V2 up to V delta, okay? And yeah, so their degrees D1, D2 up to D delta. Okay. Good. So anytime you spot some weird notation, just tell me. Okay, let me know. Thank you. Right. So okay. So back to this. Okay. So we divide the proof into two cases. Okay. So the first case is when Vn is adjacent to V1, V2 up to V delta. Okay. So the goal, okay, so let me repeat the goal. So the goal, because we want to create a graph that realizes D prime, okay, so this is D prime. So we have to remove one edge for each of these vertices. Okay, therefore their degree can be reduced by 1. Okay, and the last degree should be reduced to 0. Okay, so that's why for these vertices we should remove one edge from them. Okay, and for the last vertex we should remove all the edges. Okay, so for this case, how to achieve the goal? Exactly, okay, so just remove all the green edges, okay? So after we remove all the green edges, the degree of V1 becomes D1 minus 1, okay, because one edge is gone. And similarly, the degree of V2 becomes D2 minus 1, okay? And Vn now would have no neighbors at all. So after removing all green edges, the degree becomes D1 minus 1, D2 minus 1, up to D delta minus 1. Okay. And Vn has degree 0. Okay. And all the other degrees, they are the same. Okay. They are not affected by this modification, okay? Because these green edges do not touch them, okay? So after you remove these green edges, their degrees are the same, okay? Okay, but this is like the simple case where Vn is adjacent to these vertices V1 up to V delta, okay? So let's take a break, and when we come back, we will consider the remaining case, where Vn is not adjacent to all the vertices in this box. Okay, so we're going to see what should we do. Okay. Okay, so let's take a break. Okay.
现在可以就是用 NCT 了。
哦，OK，你说考朋友的，
我自己写。
对，好你有试结果没有？
就到1000个结语。
到1000个结语都可以是吗？
就可以算出来。哦。
不是，我说你的 MCT 设备的时候在算的时候，应该是算比较小的 case，是多少？
测到1000。
哦不，但是我们目标不是只用 MCT 设备算，我们目标是要把问题变小，然后再扩 MCT 设备。所以我一直觉得 MCT 设备那边应该不能算到很大，1000这边我觉得不太大。你现在做 TSP， 对，然后我的建议是，因为我觉得 TSP 相对也比较容易， 至少一些规定的 L 可能就被算得很好。对，所以我要你去看 independence， 你知道 independence， 他们做 independence， 对，但我希望你去做 independence， 因为 independence 是就很困难，就算规定都做不成，所以我觉得 independence 应该就比较有机会，可以比一些规定的 L。
它因为它会就是 context window 太大，
对，
所以就是你要就是放档案在外面，
放档案
就是你
在
不能直接就是把题目当成 prompt 出来。
没有问题。所以换句话说，他必须要一次读，他不能一次读完整的问题。
那这样就一定是要有那个 edge，就是程式去。
不一定吧？你可以就你那康的速度多大？你用那个？
就考
对啊
考
，20万会放不下。
测到就是7000多。
哦，因为你编的课是很多是。哦，对。7000乘7000这样子就爆掉了。就我们可以实验看看。它爆掉，如果它用一些它现成的一些压缩的方法，会，因为他们应该都会有一些去压缩 context window 的，那它应该是自动就会做，但是你如果爆掉，它会显示你错之类的。
会不会说就是可能会什么，所以他只会先处理前面。
处理完然后再处理后面。
没有。
它就不会。我觉得可以先分阶段，就是我们可以先不用做到那么大，先确保它的 context window 是可以筛一下这个问题，然后再去看。所以如果说20万是10的几次方？10万啊，10万是16次方，10的5次方，10的5次方。那我觉得我们就试100个点，然后因为100个点，对啊，这样应该够。100个点内，但是我们的那个 MCP 就算可能10个点，对，先做一下这样子看。如果它整个问题都可以筛进去，但是我也不想要直接去解，因为100个点它可能是要解很久的，对，然后你看那个他自己把它们变小，然后没有就不能用 greedy，就是要算到最佳解，就是要报进去是要最佳解。对，你可以看有没有现成的 library 可以用。对，你是用什么学 Python？那我猜 Python 应该会有一些 library 现成的，要不然就直接 bytecode 一下。那个，有一些方法，比如说你可以去解那个 mix integer linear programming，你知道吗？就是现几整数绘画。对，这个可以。然后我猜应该会有人有去设计一些比较有效率的暴力法，也可以。但 anyway，我觉得看有没有现成的，如果现成的就用现成，那如果没有的话，就 bytecode 一下，就是简单说去试所有的可能性。对，因为如果10个点的话，就24次方的用法，就可以知道哪个是最大的。对，所以这应该蛮容易，然后花的时间应该不会太多。对，好。那你回去看那些你把它看不懂那些短句，所以
我目前没有先看，我先去找其他的，就是听说我去跟那个跟人跑，
All right, okay. So case 2, okay. Okay, so what is case 2? So case 2 is the case where Vn is not adjacent to some of these vertices, okay? So it's like this edge is gone, okay? So Vn is not adjacent to some vertex in V1, V2, up to V delta, okay? Okay, so in this case, Vn is not adjacent to V2, okay? Okay, so but the goal is still the same, okay? The goal is still to remove one edge from each of these vertices, okay? And remove all the edges from Vn, okay? But apparently we cannot just remove all the edges instant to Vn, okay? Because, so what happens if this green edge is gone? So this implies that there must be some vertex, let's call it x, okay, such that Vn is adjacent to x. Okay? So can you see why? So recall that the degree of Vn must be delta, okay? So there must be delta edges instant to Vn, okay? And if for this set, some vertex is not adjacent to Vn, it means there must be some vertex outside this box, okay? Like x, and x is adjacent to Vn, okay? Okay, so what next? So our strategy will be, we want to first transform the graph, okay? To transform the graph so that after we transform it, Vn is adjacent to all the vertices in this blue box, okay? Moreover, after the transformation, the degree sequence is still the same, okay? So we do not change the degree sequence, okay? So it's like we find a different graph to realize the original degree sequence, okay? And moreover, in this new graph, Vn is adjacent to all the vertices in this blue box, okay? 也就是我们如果刚刚很理想，就是 Vn， 我们本来很理想的想象说 Vn 是连到所有的这个 V1 到 V delta，OK？ 但如果这件事情不是对的 ，OK？ 那代表说，譬如说 Vn 跟 V2 没有连起来，那这个时候我们就知道 Vn 一定是连错点 ，OK？ 所以 Vn 有连到一个点 x， 然后 x 不在里面，这唯一的可能性 ，OK？ 所以这个时候我们就不能很单纯就是把 Vn 所有的 neighbor 都把 Vn 所有的边都删掉，因为这样子像 V2 它的 degree 就不会少1，然后 x 它不应该改变它的 degree， 但它的 degree 会变小。 OK， 所以我们的目标就是我们要先想办法去改变一下这个 graph， 让这个 graph 在这个新的 graph 里面 Vn 会连到所有的这个 V1 到 V delta， 而且他们的每个人的每个点的 degree 都是一样 ，OK， 那这样子我们就可以用前面那个很简单的方法，就把 Vn 到前面这些点的 h 全部都删掉 ，OK。So the goal is to transform the graph so that Vn is adjacent to V1 up to V delta, okay? And the degree sequence is not changed. Okay. So in other words, let's just forget about this goal of like removing edges here, removing edges there. No, let's just forget about those goals. Let's focus on finding a new graph, okay? Finding a new graph such that Vn is adjacent to V1 up to V delta, okay? But the degree sequence stays the same, okay? So how to do this? Well, because we want to make sure that Vn is adjacent to V1 up to V delta, we have no choice but to add this edge. Okay, so we have to add this edge. But adding this edge creates new problem. Okay, for example, if I add this edge, then the degree of V2 is changed. Okay, it's increased by 1. Okay, similarly, Vn, the degree is increased by 1. Okay, and the second problem we have is that we want to remove this edge, right? Because we want to see that all the neighbors of Vn are in this box. So we also have to remove this blue edge, okay? But just simply removing this edge, we create new problem because now the degree of x changed, okay? It is decreased by 1, okay? So let me draw a bigger picture. Okay, so we have to remove, we have to add the edge between V and Vn, and we have to remove the edge between x and Vn, okay? We don't have any choice, okay? We must do these two steps in order to make sure that Vn is adjacent to all the vertices here, okay? And Vn is not adjacent to any vertices outside this box, okay? So we have to do these two steps, okay? But after we do these two steps, the degree of V is increased by 1 and the degree of x is decreased by 1, okay? But luckily, after we do these 2 steps, the degree of Vn is not changed, okay? Because for Vn, we first add 1 edge and then we remove 1 edge. So the degree is still the same, okay? So now we have to take care of these 2 vertices, V and X, okay? So for V, because now we add 1 edge, so we have to remove some edge from V so that the degree is still the same. And similarly for X, because we remove 1 edge here, so we're going to find a new neighbor for X, okay? So 我讲就是这边蛮有趣的 ，OK， 所以我们现在做的事情是我们必须要把这个本来不见的这个边加回去，所以 v 的 degree 会增加1 ，OK， 然后我们要把这个多出来的边删掉，所以 x 的 degree 会少1，所以我们会需要想办法帮 v 拿掉一个邻居 ，OK， 这样它的 degree 才不会改变。然后对 x 我们要想办法帮它加一个邻居 ，OK，so we need to remove one neighbor for v, and we need to add one neighbor for x. So how to do this? I'll give you a hint, okay? So the hint is that we sort the degrees, okay? So V1 has the largest degree, V2 has the second largest degree. So basically, the vertices in this red box, they have the highest degrees in the whole graph, okay? And for vertices outside this box, they have like fewer degrees in the graph, okay? And what is degree? Degree is just like the neighbors, okay? The number of neighbors. So this means for vertices in this red box, they have more neighbors, okay? For vertices outside the box, they have fewer neighbors. That's it. That's a hint. 所以我们现在要做的事情就是要帮 v 删掉一个邻居，然后帮 x 增加一个邻居，然后当然整个 degree sequence 都不能改变。那刚刚的 hint 是这个 v1 到 v delta 这个 box 里面，它们的邻居比较多 ，OK？ 因为我们刚刚排序的时候 ，v1 是最大的 degree，vn 是最小的 degree，OK？ 所以所以换句话说 ，OK？A more direct hint: the degree of v is greater than the degree of x. In other words, v has more neighbors than x does. 所以这时候要怎么做？No. So v is already adjacent to y. Yeah. So I think what you want to say is that we can add an edge here and remove this edge. Yeah, okay. Yeah, that's it. Okay. So the way we utilize this hint is that V has more neighbors. Okay. So if V has more neighbors, then we can always find a vertex that is adjacent to V but not adjacent to X. Okay? So there must be a vertex Y such that Y is adjacent to V but not to X. Okay, so I think I'm going to erase this. Okay, so this is the original graph. Okay. Okay. So to achieve our goal, we can just so this is step 1, okay? So add an edge between V and Vn. And step 2, remove this edge. And what is step 3? So step 3, we remove the edge between V and Y, and we add an edge between Y and X, okay? Okay. Okay, so let me give you a concrete example, okay? Okay. So this is the original degree sequence, okay? So this is D, and D prime is 2, 2, 2. Okay. So the way we get this D prime is by removing or making this 0, okay? And because the smallest degree, or delta, is 2, so this means for the first 2 degrees, they are reduced by 1, okay? So that's why we get this, okay? So this is Vn, sorry, Dn, and this is delta, okay? So D1, D2, D3, D4, D5, okay? So this is an example for case 2, okay? Because ideally, or for case 1 to hold, the 2 neighbors for this guy should be these 2, okay? But in this example, you can see that this guy is adjacent to this, and they are not in this red box, okay? So to make sure that V6, okay, is adjacent to V1 and V2. So what we'll do is we will transform the graph. So if we use this notation, so this means I want to make sure that Vn is adjacent to some vertex in this box, and let's call it V. So for example, V can be this vertex, okay? A vertex in the red box that is not adjacent to Vn, okay? So instead of being adjacent to V, Vn is adjacent to X. This is like a wrong neighbor. So in this example, V4 can be X, okay? So we want to make sure that we can remove this edge. And we can create this edge, okay? But we cannot just add this edge and remove this edge because it changes the degree sequence. So what we will do is that we're going to find a spatial vertex Y, okay? So Y is a neighbor of V, but not adjacent to X. So in this example, what is Y? So which vertex can be the spatial vertex Y, which is adjacent to V, but not adjacent to this guy. So it can be, you can choose either this one or this one, okay? So this can be Y, okay? Because Y is adjacent to V, but Y is not adjacent to X, okay? So we will remove this edge and add this edge. Okay, let me draw the new graph. Okay. Well, I think I can just, yeah, that's it, okay. Okay, so same degree sequence, okay, 3, 3, 2, 2, 2, 2. We have V6 is adjacent to this one in the red box, okay. So that's basically what the proof does, okay. But we haven't reached case 1 yet, because to reach case 1, we have to make sure that all the neighbors of V6 is adjacent to vertices in the red box, okay? But still you can see that there's this wrong neighbor again. So if you want, we can do this again. So X is the wrong neighbor, okay? And V1 is the correct neighbor for V6, okay? So in this case, which one can be Y? Which vertex can be Y? 我们刚刚不断做的事情就是去 identify 错误的 neighbor， 就是它不是在那个 V1 到 V delta 里面 ，OK？ 所以这是 X，OK？ 然后去 identify 一个正确的 neighbor， 但是我们现在还没有连过去。OK， 我们想办法连过去这样，所以这个例子就是 V。那我们刚刚的做的事情是，我们都要想办法让我们的 V6 真的可以连到那个 V， 而不是 X。所以我们会在这个 V6 跟 V 之间加一个边，然后 V6 跟 X 的边删掉。当然，为了要这样做，我们就需要去删掉 V 的一个邻居，然后帮 X 增加一个邻居。我们要怎么做？我们就要想办法找到 Y。所以 Y 是 V 的邻居，但不是 X 的邻居。所以这个时候 Y 可以选谁？第三个，这个 ，OK， 所以为什么？因为这个点它跟 V 是邻居，它跟 X 不是邻居 ，OK， 所以这个可以当 Y，OK， 所以我们要做的事情就是四步。OK， 第一步，把正确的边、正确的邻居加上去。然后删掉错误的邻居。OK， 然后接下来我们就需要帮这个错误的邻居再加一个边，就是 X 跟 Y 之间。然后最后我们要帮我们正确的邻居删掉一个邻居。OK。OK， 所以做完之后，这图就会变这样。OK。So now we really reach case one because first of all, degrees are the same, and Vn is adjacent to exactly all the vertices in the red box, that is V1 up to V delta. Okay. Okay, so that's basically the proof. Okay. So if we can achieve this goal, which means we can find a new graph, okay, such that Vn is adjacent to all the correct neighbors, then it reduces to case one. Okay, so we just then remove all the green edges, okay, to get the desired new simplified degree sequence D prime. Okay. Okay, so that's a proof. 大家对这个 proof 有问题吗？所以我们刚刚做的事情是，我们先考虑一个比较简单的 case，OK，、然后在这个简单的 case 里面，我们可以假设就是 Vn 就是跟 V1 到 V delta 都是相连。那在这个 case 里面，我们只要很简单把这些绿色的边都删掉，我们就可以变成 D prime，OK。但如果这些绿色的边也有一些边不见 ，OK， 我们就需要去把我们的图稍微转换一下，想办法把绿色的边加进去 ，OK， 然后把错误的边删掉。有问题吗？OK, good. Okay, so recall that one of the motivation for studying graphical degree sequence is that we want to create graphs to, for example, do some experiment. But sometimes we do not want just to have any graph, okay? We want to have a kinetic graph, okay? We want to make sure that the algorithm produces a kinetic graph instead of disconnected one. So next, we're going to study like an extended version of the problem. That is, we want to make sure to create kinetic graph, okay? Okay, so here the key word that I'm going to define is potentially connected, okay? So potentially connected means, so if a degree sequence is potentially connected, this means not only that this is graphical, okay, but we can also find a kinetic graph to realize it, okay? Okay. So let me give you some example, okay? Okay, like this one, okay? So 5 twos, okay? So this one can be realized by a kinetic graph, like this. Okay? But I want to stress that this does not imply that any graph that can realize this degree sequence must be a kinetic graph. So this definition only requires that there's like one graph, one kinetic graph can realize it, okay? You don't have to make sure that all the graphs that can realize it are connected, no, okay? Because for this one, you can also realize it by no, I think, sorry. Let me add one more 2, okay? So 6 twos, sorry. Okay. So you see, there are 2 different graphs that can realize the same degree sequence, okay? So some of them disconnected, some of them connected, okay? But still, this is a potentially connected degree sequence because potentially we can find a graph, we can find a kinetic graph to realize it, okay? So that's why we have this word potentially, because not all graphs are connected, okay? I mean, not all the graphs that can realize it are connected, so yeah. Okay, and some current examples. So this one is not potentially connected because the only way to realize it is by this graph, okay? And this one is not connected. So yeah, this is not potentially connected. Okay, so we're going to study like two versions of problems related to potentially connected. So first, recall that for graphical degree sequence, there's no simple check to test whether it is graphical or not. But for potentially connected degree sequence, if given that we already know the degree sequence is graphical, okay? So that's our assumption, okay? We don't have to check it. We know that it is graphical for sure, okay? But we want to test whether it is potentially connected, okay? So it turns out that given a graphical degree sequence, to test whether it is potentially connected, it's very simple, okay? So okay, so the assumption is that it is graphical, okay? So we don't have to test whether it can be realized by a graph, okay? Okay. So can you guess what kind of properties we need to guarantee potentially connected? Just by looking at the degree sequence, okay? So D is just D1, D2, up to Dn, okay? So what can you say about a graph or about the degree sequence for some connected graph? 所以如果一个 graph 它是 connected， 那有什么特性是很简单你可以看得出来，然后这特性是跟 degree 有关的。Okay. So D1 is greater than 0, D2 is greater than 0. Okay? So we cannot have vertices without any neighbors, okay? Otherwise, it must be disconnected, okay? But can I say that as long as all degrees are at least 1, then the degree sequence must be graphical? Oh, sorry, must be potentially connected. No, because we just saw an color example, right? So if all degrees are like 1, okay, still not graphical. Oh, sorry, not potentially connected, okay? So we need more constraint. So perhaps I'll change this to at least 1, okay? So what else do we need? So the problem with this property is that at least from our previous corner example, the problem is that the edges are too few, okay? Right. So I think an easy way to think about this is if a graph is connected, then the graph must contain a spanning tree. Okay? So if you have, say, 10 vertex graph, okay, then what is like the smallest number of edges you must have in order to create a connected graph? 如果你这个图有10个点，然后我跟你讲这个图一定是 connected， 那这个图至少要几个边？9 ，OK？ Okay. All right, so you can draw some example to convince yourself. So basically, we need to create a tree, okay? So, yeah, so here we have 8 vertices, okay? And 7 edges, okay? So I think it's quite easy to tell that if you have m vertices in your tree, then the number of edges is exactly m minus 1. Therefore, if the graph has m vertex and it is connected, then the graph must have at least m minus 1 edges because it contains the spanning tree, and also it may contain other edges, okay? So this is at least. Okay, so edges transferring to degrees. It's like a factor of 2. So if you have at least m minus 1 edges, this means you have twice the number of edges. Okay, so 2 times m minus 1. Okay. Sorry, this is. Okay. So this means d1 plus d2 up to dn is at least 2 times m minus 1. Okay, so this is not a proof, okay? So basically we just, it's like we have this direction, okay? So if we already know that this is a potentially connected graph, also a potentially connected degree sequence, then for sure we cannot have 0 degrees. And since it can be realized by a connected graph, so their total degree should be at least twice m minus 1, okay? So we already have this direction. Now we have to consider the other direction. Well, even though this is easy, but for completeness, I think, yeah, I'm going to write down the proof. Okay, so first step, okay, so just by the definition and the assumption, okay. So the assumption is that D is potentially connected, okay. Okay, D is potentially connected and D is graphical. So this means, first of all, there must be a graph that can realize D because it is graphical. And secondly, because it is potentially connected, so we can find a kinetic graph to do this, okay? So since this is connected, there's no isolated vertex. Recall that an isolated vertex is a vertex without any neighbors. Okay. So for example, if this is a graph, then this guy here is isolated. Okay. And if there's no isolated vertex, then all degrees must be at least 1. Okay? Okay. So let's call this kinetic graph G. Okay. So all degrees in G are at least 1. Okay. And because G realizes D, so the degree sequence of G matches the degree sequence D. Okay. Okay. So this step is due to G realizes D. Okay. Okay, so this is the first property. And the second property, okay, so go back to here. Okay, so the graph G is connected. So G has a spanning tree. Okay. Therefore, G has at least m minus 1 edges. Okay. Therefore, the total degree of G is at least 2 times n minus 1. As a result, the total degree, of D is, again, 2 times n minus 1. And for the last step, we also utilize this. Okay. Okay. So basically, what happens on G also happens on D. Okay. Because G realizes D. Right, so yeah, so that's the proof for this direction. So let's take a break, and then we will consider the other direction. Okay. And I think the other direction is like more interesting. More interesting. Okay. Okay, so let's take a break. Okay. So next, we're going to consider the proof for the other direction. But let me first write down the statement. Okay. So we still have the assumption that the degree sequence is graphical. Okay. So yeah, basically our discussion do not consider the case where it is not graphical. Okay. So we have two properties, okay? And this time they are the assumptions, okay? And what we want to derive from these two assumptions that it is potentially connected, okay? But this time I'm going to just write down the meaning for potentially connected, because if D is potentially connected, this means it can be realized by a connected graph. Okay. Okay, so actually the proof is also quite easy. Okay. So we're going to start with this assumption, okay, because D is graphical, so we know that we have some graph that can realize D. Okay. Okay, so the reason we can write down this is because D is graphical. Okay, this is our assumption. And so it's like we still have two cases. And the first case is trivial. So if this G is connected, then we're done. Because the goal is to show that it can be realized by a kinetic graph. So if it just happened that this G is connected, then the proof is done. Okay. So in other words, we only need to consider the case when G is not connected. Okay? Because if G is connected, the proof is just too trivial. Okay? So we only need to worry about the case where G is not connected. Okay. Okay, so let me give you an example. So this is G, which is not connected, okay? And so what is the degree sequence here? So D is 4, 3, 2, 1, 1, 2, 1, 1. Okay? 4, 3, 2, 2, 1, 1, 1, 1. Okay? And you can also check this degree sequence satisfies these two properties. Okay? So clearly there's no isolated vertex, and all degrees are greater than 0, and we can count the total degree. So the total degree, so what is the total degree here? No, this is, no, this is 3, sorry. Okay. 14, okay, is the total degree. So what is N? N is 8, okay? So 2 times N minus 1 is exactly 14, okay? So the total degree is large enough, okay? And there's no isolated vertex, no 0 degrees. So if the statement that we try to prove is correct, then we should be able to find a kinetic graph to realize it, okay? Okay. So back to the proof, okay? So now we have a graph. We can always have a graph for a graphical degree sequence. So this is our graph. Unfortunately, this is not connected, okay? So this means we have to transform the graph again, okay? But for a different purpose, okay? So now this time we have to transform the graph so that they still have the same degree sequence, but this time they are connected, okay? Okay. So degree sequence is not changed, means the degree sequence is still D. okay? Because D is our input, and we want to find a kinetic graph to realize it, okay? All right, so let's first consider this example, okay? So for this example, how to transform it, how to modify it so that it becomes kinetic without changing the degrees. 所以我们现在的目标是要把这个 graph 变成是 connected，OK？ 它需要2个 component，OK？ 对，很明显不是 connected。所以，然后另外一个限制是 degree sequence 要一样 ，OK？ 不能改变。所以要怎么做到这件事情？So actually, I can replace this degree sequence constraint into a stronger one. That is, I want to make sure that every vertex okay? So actually, for this transformation, we will not change the degree for every vertex, okay? So for this, originally it has degree 2, so after we transform it, it still has degree 2, okay? This one, after we transform it, the degree is still 3. Okay. 所以要怎么改？应该不会太难。当然，我需要有一个比较有系统的方法，而不是有点 ad hoc，OK？、因为某种程度我要把它变成一个 proof， 所以要怎么转换？Well, naturally, because there are 2 components, to make it kinetic graph, it's like we have to create some bridge between these 2 components. Okay. In other words, we have to add some edges between these 2 components. Okay. But we cannot just add edges because adding edges change the degree. Okay. So not only that we have to create edges, we also have to remove edges. Okay, to make the degrees unchanged. So how to create and how to remove edges. So 我们铁定要建一些类似桥梁的东西 ，OK？ 但建桥梁就代表你要加 edge， 加 edge 就代表 degree 会变大 ，degree 变大就代表你违反限制，因为我们刚刚说 degree 要不变，所以如果要确保 degree 不变的话，我们除了加边，就还要拿掉一些边。所以要怎么样拿掉一些边，才可以让最后的 degree 是不变的？有任何想法吗？I'll give them. I'm sorry. Sorry. Let me first label these vertices. Okay. A, B, C, D, E, F, G, H. All right. A, F, and C, G. Okay. A, F, C, G. Okay. A, C, and F, G. And yes, so after create these two edges, removing these two edges, we get a connected graph without changing the degree sequence. All right, but so it seems like first we have to create two edges, okay? And then we just remove the like two corresponding edges, okay? So, but how to find these two edges? OK cycle OK 有 cycle 的那个exactly OK exactly OK so the critical observation is that if you have a cycle OK then actually you can remove any edge on the cycle like this AC so even if you remove this edge the left component is still connected, okay? Because you can use the other edges on the cycle to remain connected, okay? And after that, things are just easy. So for the other component, you can actually remove any edge. It doesn't matter if it disconnects the graph after you remove it, okay? Because then we'll create these two bridges, okay? So these two bridges will then once again merge these two components, okay, using these two bridges. Okay. So the key point is to find a cycle and find an edge on a cycle. So find a cycle C, okay, on G, and pick an edge. Let's call it UV on C. And pick another edge. Let's call it XY on a different component. Okay, and then we just remove these two edges and connect these two edges. Okay, so more precisely, we remove UV and XY, and we add UX and VY. Okay, so we have two components, and we have a cycle. Okay, so this is the cycle C, and we first find, after we find the cycle C, we find, or we pick any edge on the cycle. Okay, and then we find different components and pick any edge on the new component, XY, okay? And we just remove these two edges and create the bridges. Okay, so this is our algorithm, but let's go back and review the statement that we try to prove, okay? So we want to prove that if the degree sequence is graphical and it has these two properties, then it can be realized by a kinetic graph, okay? But the algorithm here, it needs a cycle, okay? All the rest are easy, okay? Because after you can find a cycle, definitely you can find an edge, and if the graph is disconnected, you can certainly find a different component, and all right. So perhaps we can first think about this, okay? So in the third step, we can always find a different component because the graph is disconnected, okay? Recall that we only need to consider the case when G is disconnected, which means there must be multiple components, at least two, okay? So we can for sure find a different component, but is it always true that we can find an edge on a component? So is it possible that we have a component without any edges? So a component without any edges is like this component. Okay, so this is also one component. Okay, but do we allow this kind of components in our proof? So this is our assumption, and we have a graph G that realizes the degree sequence. Now, in this kind of graph, even though it is disconnected, even though it has multiple components, is it possible that this G has a component that only contains a single vertex? No. Why? Exactly. Because G realizes D, and we know that in the degree sequence D, every degree is at least one, meaning every vertex has at least one neighbor. Therefore, every component has at least one edge. So this step is always doable because every degree is at least one. Therefore, every vertex has at least one neighbor. Okay. And the last step is certainly doable because we just remove and add edges. Okay. So we have two properties here, and so far we've used the first one. Okay. And where should I apply the second property, that is the total degree is large enough. Can I always find a cycle in any component? Well, not necessary because say if I remove this vertex, oh sorry, this edge, okay? So this is a component without any cycles. So it's possible that a component has no cycles, okay? But we have this, okay? So this says the total degree is large enough, okay? So intuitively, if there are lots of edges, okay, in the graph, then we should be able to find a cycle, okay? That's the high-level idea, okay? But we need to prove this, okay? But the result is that this is always doable because the total degree is at least 2 times n minus 1, okay? So we're going to prove this, but this is the high-level picture of the proof, okay? So let me go through the proof again, okay? So start with a graph. If the graph is connected, then the proof is done. And if not, if the graph is disconnected, then we can merge components, okay? So to merge components, we first find a cycle. And turns out that if the total degree is at least twice n minus 1, you can always find a cycle, okay? We're going to prove this later, okay? And after we find a cycle, we just find any edge on the cycle. And then we find another component and find any edge on the other component. And it turns out that we can always find a edge in any component as long as the degrees are at least 1, okay? And then we can just modify or transform the graph so that we can merge the components, okay? So after do this once, we merge 2 components. So you have more, if you have more than 2 components, you just repeat this process, okay? Until all the components are merged into 1. Okay. All right, so we're going to prove this, okay? But before we prove it, let's consider a simpler problem, okay? That G be a kinetic graph. Okay. So let's first consider this, okay? So for example, if you have a kinetic graph, okay, and the kinetic graph has 10 vertices, and also it has at least 10 edges, is it true that the graph must have a cycle? We can try, okay, so perhaps you can try a small example like n equals 4, okay? So you have 4 vertices, right? And you have at least 4 edges, then you must have a cycle if the graph is connected. But still, I want to have an argument for this, okay? 所以为什么只要你有 n 个点，然后你至少有 n 个边，然后你是 kinetic graph， 你就一定会有一个 cycle。来考验一下我的记忆力，是诗与嘛 ？OK， 好，我记忆力还不错 ，OK。所以为什么？ OK。好，我忘记了。对，所以这个是你的名字是郑浩。OK， 所以郑浩有 idea。如果没有 cycle 的话，最多是 n 减一个变。对，那为什么？想法吗？complete trees 是什么事？啊哈，啊哈，非常接近，但是这 argument 有一些不是很顺的地方。OK， 但确实这边有一个关键是。So because G is connected, so G contains a spanning tree, okay? And because a spanning tree with n vertices contains n minus 1 edges, so G has at least n minus 1 edges. Okay? Okay, so this is a tree, okay? So a very important observation is that if you have a tree and if you add any edge to this tree, you'll create a cycle. For example, you can add this one, then you'll get a cycle, okay? Or you add an edge here, you get a cycle, okay? And you add an edge like this, also you get a cycle. But why? Why is that after you add any edge, you get a cycle? So because this is a tree, meaning you can go from any vertex and using the edges on the tree to reach any other vertex. Okay? For example, you can go from here and then use this edge and reach this one. Okay? So the edges on the tree already define a path between any two vertices. Now if you add one more edge between the start and the end vertices, it's like you close a path, okay? Therefore you create a cycle. Okay. Okay, so because now we've established that G has a tree, and we also know that G has at least n edges, not just n minus 1. So G contains some edge that is not on the spanning tree. Okay, so let's call this spanning tree T. Okay. So this edge, along with the edges on the spanning tree T, will create a cycle. Okay. So that's the proof for this warm up. Okay. Okay, so basically it says that if you have a kinetic graph and you have at least n edges, okay, then you can always find a cycle. Okay. Okay, but this is not our goal. Okay. Our goal is to show that we have a disconnected graph, okay, not a connected one, okay. And want to show that if the total degree for the whole disconnected graph is at least twice n minus 1, then there must be a cycle, okay. So we have a disconnected graph and a total degree is at least n 2 times n minus 1. Okay. So we want to show that it must have a cycle. And to do this, we can use this result. Okay. So all we have to do is to show that we have a component, and in this component, the number of edges is at least the number of vertices. Okay. Then by this result, we get that this component has a cycle. Okay. So let's assume that we have component H1, H2, up to HK. Okay. So some notations here. Okay, so because it is disconnected, so there are multiple components. So I'll just write H1, H2 up to HK. So we have K components, and K is greater than or equal to 2. Okay, because it's disconnected. Okay. So here I just define Ni as the number of vertices in Hi and Mi as the number of edges in Hi. Okay. So the goal is to find some cycle, and according to our previous discussion, to have some cycle, all we have to do is to show that there are some components, and in this component, Mi, that is the number of edges, is at least Ni, that is the number of vertices. Okay, so all we have to do is to show that we must be able to find Hi, such that Mi is greater than or equal to Ni. OK， 所以我们前面已经有说，就是这个一个比较简单的 property， 就是只要边的个数至少是点的个数，你就一定可以在这个 graph 里面找到 cycle。OK， 当然这问题是这个是 kinetic graph。OK， 当我们前面的这个 algorithm，它 apply 的是一个 disconnected graph。OK， 所以不能直接用我们刚刚前面的这个 warm up 的结果。但是我们可以说的事情就是想办法。去找到一个 component， 因为 component 本身就是 connected，OK， 所以如果可以找到一个component， 然后它的边的个数至少是点的个数，那我们就可以说这 component 就会有 cycle，OK， 所以这是我们刚刚这边要 set up 要做的事情，就是前提是我们有一个 disconnected graph， 然后我们已经知道它的 total degree 至少是2倍的 n 减1，OK， 我们刚刚已经有说了，我们会利用这个性质 ，OK， 然后基本上这边就是我说的 components，OK。然后我们要找到这些事情，找到这个 Hi。OK。OK。So it's quite easy, okay? So we're going to prove this by contradiction, okay? In other words, we're going to assume that we cannot find such a component Hi. In other words, every component, for every component, the number of edges is at most Ni minus 1, okay? So for any component Hi, the number of edges is at most the number of vertices minus 1, okay? So whenever you see this, you can think of, whenever you see minus 1, think of a tree, okay? So this component is like a tree, so no cycle, okay? And what we do here is that we want to show that there must be a cycle, there must be a component such that it not only contains a tree, it also contains some edge that is not on the tree. Therefore, it has Ni minus 1 plus 1. So it has Ni edges. So what we do here is that we prove it by contradiction. So we assume that this is wrong, okay? In other words, every component has at most the number of edges as a tree, okay? So we have this, okay? And we want to find a contradiction, okay? And so the total degree or let's count the total edges. So this is just M1 plus M2 up to Mk, okay? So this is at most N1 minus 1 plus N2 minus 1 up to Nk minus 1, okay? So this equation holds because how to count the number of edges in the whole graph? We'll just count the number of edges in every component, and add them up, so we get this, okay? And why can we have this? And this is because our assumption, okay? So every component is like a tree, so the number of edges is at most ni minus 1, okay? Okay? And here I just put together all these ni terms, so n1, n2 up to nk, okay? And because there are k components here, so we have k minus 1. So in total we have minus k. Okay? Now, can you see how to get the contradiction? So first of all, what is this sum? n1 plus n2 plus da 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 plus nk. So what is this? So recall that n1 is the number of vertices in the first component, n2 is the number of vertices in the second component, and so on. So adding all this up equals just the number of vertices in the whole graph. Okay? So the whole picture is like this, okay? So we have H1 here, H2 here, H3 here. So here we have N1 vertices, M1 edges, N2 vertices, M2 edges, okay? So here we just consider the sum of all the ni's. So it's just the number of edges, sorry, the number of vertices in the whole graph. Okay. Okay. So now we get that the total edges, the total number of edges in the graph is at most n minus k. So this means the total degree is what? So if we get the number of edges is at most n minus k, what is the total degree? It's just a difference of factor of 2, okay? So multiply the number of edges by 2, you get the total degree. Okay? But we know that k is at least 2 because we have at least 2 components. So this is at most 2 times n minus 2. So we get the result that total degree is at most 2 times n minus 2. And this is a contradiction because we know that in our assumption, the total degree should be at least 2 times n minus 1. So that's a contradiction. Okay?有问题吗？所以，这边的直觉比较像是，如果我们一开始的这个 degree sequence， 它的 degree 是够大的 ，OK？ 那就算我们一开始的，我们随便画一个 graph 去 realize 它，就算我们画出来那个 graph， 但不小心画的是 disconnected graph， 那我们都可以确保说，我们一定至少在某一个 component， 它有足够多的边。因为本来的整个图的 total degree 是够大，换句话说就是本来图的边的个数是够多的。那如果本来的图边的个数是够多的，直觉上来讲就一定会有一个 graph， 一定会有一个 component， 它的边是超过要去建一个 tree 所需要的边。那这个时候就代表它有一些边是不在这个 tree 里面，所以它就可以产生 cycle。OK， 所以我们刚刚做这个 proof 只是比较 严谨的去看这件事情，就是我们用反证法，如果真的每一个 component 它都不会有那种超出 tree 的边 ，OK， 换句话说，它们的边的个数最多就是点的个数减1。那这样子你就会发现，其实根本一开始就不会有那么多个边，所以就有矛盾 ，OK。Okay, so this completes the proof, okay? But, and also I think this is, the proof can be transformed into an algorithm for finding a kinetic graph that realizes a potentially connected degree sequence. So what you can do is that you first apply the algorithm we've discussed for the graph realization problem, okay? And if the algorithm returns a disconnected graph, all you have to do is to apply this algorithm to merge components, okay? So this is one algorithm to find a kinetic graph to realize it. So in the next week, we're going to show that actually we can use a simpler algorithm to do this. And this time, the key point is step A. Okay, so next week we're going to show that if we're more careful when we pick this vertex in step A, if this Vj is the one that has the smallest remaining degree, then the algorithm will always output a kinetic graph for any potentially connected degree sequence. 就下礼拜我们会去讲，如果我们在这个 step A 选的这个 vertex 不是随便一个 ，OK， 这边我们都随便你想选哪一个都可以。那如果我们选的这个是 remaining degree 最小的那一个，那我们可以保证说最后 output 的 graph 一定会是 connected，OK， 当然前提是我们的 given 的 degree sequence 是 potentially connected，OK， OK， 好，所以我们今天就上到这里。